because people could provide a response that indicated more than one of these things. And so some of the other responses they gave were move to a different location, avoid risky areas, assess the situation, be alert in case something happens, seek more information, it depends on the situation, all those kinds of things. And so all of these really are also correct responses in a way. For example, this is a National Weather Service campaign because a lot of people in the US that die in flooding die in their cars when they go into or get stuck in rising water. So avoiding risky areas is important, and all these different things can be things to do, you know, that can help you avoid the risk depending on the situation. So people generally got this climate safety message as the first level, but there's other things that one can do, and so looking at these responses in more detail, these are some examples of the actual responses people gave. So some people said kind of the standard response, climate safety, go to higher ground. Then some people talked about how to do climate safety, so get to higher ground and hold on, climb a tree, get as high as possible, whatever that means, where you are, you know, famous run like nuts, depending on where you are, how fast you can run, and so on. There are other examples that people gave, like move out of canyon areas, so move out of an area of high risk, and that is a good thing to do. You have enough time to do that, and there's no flooding on the way. Stay away from creeks and rivers, also very good advice. Keep your eyes open, be cautious. So people that were saying that if you hear a flash flood, you should really be alert to what's happening in your situation so you can know if the flooding's going to happen for you. Because with these kinds of rapid events, often the warning might cover a large area, but it might not affect where you are, and so you need to assess whether you're just using environmental and social cues. And the same is true for tornadoes and other kinds of convective events, that often the warning might cover a large area, but there's only a small part of the area that's actually at risk. And then some people gave these other kinds of responses, like it depends on where you are, or have high ground picked out nearby, go to it because you want to be running. That sounds pretty good. Or think, assess the vulnerability of your location and act accordingly. So really look around you, try to figure out where to flood, and so on. And so this really reflects the complexity of decision-making in this kind of situation. And so as I mentioned, we conducted this survey before we had this flooding in our area, and then we had this flood event where actually, where I lived, we were under a flash flood warning for a lot of 4 days. And I never saw flooding myself. And so it really, and I talked to people that I know living in my area about the decisions they made, and it really kind of emphasized the complexity of making decisions in these kind of rapidly evolving environments. In fact, we talked to some of the local public officials that are involved in emergency management in one of the communities afterwards, when the communities got affected, and they said that when the flooding first started happening, they got calls from people who lived kind of in the hills above the town, and they said, what should I do? It was nighttime, they knew there was flooding somewhere, but the public officials didn't even know where flooding was. The Weather Service didn't know where flooding was. They didn't know which roads were out yet. They didn't know where the heaviest rain was falling. They didn't know which area really was. And so the emergency managers talked about how they couldn't tell people what to do. They couldn't say, is it okay to stay in your house? Should you go to the second floor? Should you try to drive out? Do you need to go outside and go up the hill? And I'll show some pictures in a minute that really illustrate this, that in this kind of rapidly evolving situation where the hazard is rapidly evolving, there's a lot of spatial variability, especially when you get down to the details of where people are with the most hazards. And the vulnerability is really situation dependent. Where is your house? What kind of house do you live in? Are you in your car? Is your family there? What kind of do you have medical needs or other kinds of things? Really leads to a lot of complexity and uncertainty in risk assessment and protective decision making. So on the top here, there's, for example, examples of pictures that happened during the flooding in our area that happened a few years ago. You can see this is an example. This actually happened at night. We're just driving, and then the road was gone. They didn't know it. No one knew the road was gone. They just drove off the road because it was gone. This was not far from my house. This is an example of a house where half of it fell into the creek. So if you're on this side of the house, you're fine. If you're on this side, you're not. And it's not clear, like climbing this tree wouldn't have been a good idea. Maybe this tree would have been okay. And here you see, here's an example of a road that's washed out with cars, but yet these houses on the hill are totally fine. They don't have any problems, whereas this house wasn't. And so in this kind of situation where there's a lot of uncertainty, spatial uncertainty, temporal uncertainty, uncertainty about what's happening, that really translates through into how people are assessing the risk, what kinds of information they need to use beyond the warning messages. But even people with the most expertise, the forecasters and the emergency managers, didn't really know what was going on until kind of after some of it was happening. And so this really emphasizes the complexity and uncertainty in how people are evaluating the risk and how the uncertainty in the weather forecasts, some of which is fundamental about picking these kinds of detailed things that people want to know because they want to know what's going to happen where they are, how that translates through into how people interpret the messages in their decision making. And so the example I've shown here is about a really rapidly evolving, highly uncertain situation, but I think some of it does extend to other kinds of weather situations. It's just maybe not as time compressed, but there still is that uncertainty about what's actually going to happen where you are, and what does that mean for how you think about the risk and what you decide to do, with the idea that all this information is rapidly evolving. And when you have something like a hurricane or a synoptic event or winter storm, you really see that play out over the period of days sometimes as people get new information and make decisions and so on. So this raises the question that is another thing that we're thinking about that I think is important going forward is how do we communicate about risk, and also about the protective options. So the first level response is turn around, don't, or first level recommendation is turn around, don't drive. So don't drive through a flooded area. And seek higher ground. And that's good first level information. But as people told us in our survey, how to actually implement that can be really difficult and situation specific. And same with evacuation, or say a hurricane or something else. So evacuation is what you want people to do, often if they're at high risk, but how they do that, when they do that, where they go, do they evacuate to some place that might end up being riskier, and so on. Those are all important things to consider when giving recommendations. So really, how do we communicate about the risk and the uncertainty, and how do we communicate about the best things, given the complexity and the uncertainty. So going back to the overview of my talk, I really focused on the link between weather messages and action and the different complexities in that, and some of the ways that we think about that in our research and other people who do research in this area. And of course, the link goes both ways, as I mentioned. So you also want to think about action and what you want people to do at the end, and how that goes back to the messages that you need to provide, and how those are going to kind of translate through into action. That's important to think about for designing messages. So I talked about how people interpret and use weather forecast and warning information. I talked first about how different people interpret and use information differently, and some of that's because they just have different interpretations and different risk tolerances and experiences and so on. But some of that's because their actual situations are different, based on where they live, or what their constraints are, or where they have to drive to go from home to work, those kinds of things. So some of that is sort of in their minds, but some of that's really in their lives and their different vulnerabilities and the different kind of contexts of their lives and resources and so on. I talked about how people's decisions are influenced by many different factors. So there are these things that happen between weather messages and action, their interpretations, their feelings about the situation, there are other kinds of beliefs. There's information that people get along with the weather messages. There's a lot of things that kind of go along with the action or their responses, along with just that final decision to evacuate, say, or take some protective action. There's things they do before that enable that. There's other kinds of responses they can have, like seeking more information or sharing information. And then, as I really talked about, in today's world especially, communication, interpretation, and decisions are complex, interactive, and evolving. So most people are really highly interconnected in today's world. They're getting information from all kinds of different places. In our Twitter data, we really see that some people are getting information sort of firsthand from a meteorologist or from an emergency manager, but a lot of people are just getting information from other people. They're seeking information from other people, they're getting it from other people, and that's a lot of what they're using to assess their risk, and all of that is evolving at the same time as their interpretations and their decisions. So last, I'll just briefly talk about some things about what this means for weather communication in today's world. I want to emphasize that this kind of complexity has always been there. So people have always been using information in complex ways. They've always been using environmental cues and cues from their social environment to make decisions. But it's getting that much more complex with today's interconnectedness and all the information that's available, and the more detailed weather forecasts that we can provide further in advance, and also the diversity of information you can get from different sources. So it's all getting that much more complicated, and it's changing all the time. So you can study something now, and in a year, it's going to be a different platform people are using, or a different kind of information, and so on. So it's kind of a moving target. So these are some ideas for going forward. The first is that there's not one best way to communicate. Sometimes we think that we can just find the right kind of messaging, that we can kind of address these problems of convincing people to evacuate. So in the U.S., for example, for hurricane evacuation, there's been a big emphasis on communicating storm surge information in the weather service, and they're trying to find ways to do that. But because of the diversity of people's interpretations of decisions and their situations, there's not one message that's going to reach everyone. So we really need to think about the diversity of reaching people where they are in different places, and they're going to get information from different sources. It's also important to consider weather messaging in context. I mean, a lot of the research that we do and that other people do really focuses on people's responses to one piece of information at one time or decision. And that's really useful research and guidance to think about these more complex situations, so you can learn things in those simplified situations to interpret things from the more complicated world. But in reality, any given piece of information, so for example, this potential storm surge map, it's only useful in the context of everything else we've already done. And we've done some research recently where we tried communicating about different hazards associated with the landfall and hurricane in simplified ways, but we found that information about flooding or storm surge didn't really affect people's decisions because we believe that most people, when you just give them the information about the wind, the people that are going to evacuate, a lot of them already decided to evacuate based on that. And so the additional information about flooding or storm surge that we gave them didn't provide additional information for them to identify whether they were high risk and convince those who hadn't already decided to evacuate to do so. So it's really important to think about any piece of information in the context of everything else, especially in today's world. You really can't think about any piece of information outside all the information people are getting from other sources. Another kind of recommendation is to meet people where they are. So because of this diversity, the diversity in their sources, different ways they're getting information, different ways they're proceeding it, the different decisions they need to make given their situations, it's really important to meet people where they are and the decisions they're making and what they're doing. So instead of going from this is the information I want to communicate, how do I get that out? Think about what do people need to know and how does the information I can provide or that I can't provide kind of project onto that, and how can I extract from what I can predict the most useful thing for people where they are, and also where they're going. So this situation is the kind of modern information environment is evolving really rapidly. We work with people who focus on social media, and they talk about how when they study something different is going to be there in 6 months or a year. So people are kind of inventing new things all the time, so you have to kind of think about where people are going and know that this is going to evolve, and the kind of solution now might not be a solution for a few years from now, and kind of even provide messaging in the context of the fact that things are going to be changing. And I wanted to just mention at the end that research can help build robust understanding. There is research in this area, whether it's communication in the US, in the UK, and other places, but there's still a lot of work where someone will decide to produce a message and put it out there and just see what happens. And so that can be really useful, where you can test the message on your grandmother or your dentist or someone to see what they say. But really one of the advantages of doing research in this area is that you can build robust and more generalizable understanding that's less anecdotal and really understand what's going on as opposed to kind of what you think is going on in the first picture. And we've really seen that with hurricane evacuations. There's a lot of talk about why people didn't evacuate or why they did. But there's a lot of different factors in understanding that research can really help using multiple approaches, theories, and methods. So there's different theories and approaches from the social sciences and other fields that can really help with this, and different kinds of methods. So I talked about return data analysis, there's surveys, interviews, and other kinds of methods that you can use to understand this. But by bringing them together, you can really build a more robust understanding than you can by just producing something and asking 1%. And I think that's an important way for the community to go forward that people are focusing on that. So I will stop there and take some questions.
Actually accepted that there was quite a range to that.
Right.
That research was from like 10 years ago.
Right.
Do you think that's still the same just now?
Yeah, I think it is. There was a study, I think it's published in Weather by Patchy et al. that reproduced that in the UK. That's probably 4 or 5 years ago now. There's been some work in Europe and kind of more detailed work along those lines. But I think that it still is. I think that, first of all, it's still true that the forecast is 75 degrees. The temperature isn't precise. I think that even as weather forecasts get more accurate, people are sort of behind in terms of their experience and how they interpret that. They think the perception of how accurate the forecasts are is still kind of behind because of their experience. So right at the same time, for example, when Hurricane Irma was approaching the coast, even though that was a really good forecast by meteorological standards, it was much better than the forecast that we did 10 or 20 years ago, people still wanted it to be better. So some people do have these expectations that the forecasts really are quite accurate now, and that probably has changed in the last 10 years. So we haven't done it, but I guess our evidence from other kinds of situations suggests it's true to some extent that people do have a much more detailed
you showed that plot where the hurricane was about to sort of make landfall and day 5, 3, and 1 and so on. I was just thinking, you can imagine a situation where at day 5, the probability of it happening in your location is quite low. And maybe you have lots of options for what you can do then. But as time goes on, the probabilities may start to rise, but your options become more and more limited. The roads are starting to get blocked and things.
Right.
And so you could end up in a situation where you just stay put.
Right.
But, not able to make a decision the whole time. I don't know if that happens or whether
yeah.
there's a way of getting out of that.
Yeah, it definitely does. I mean, that's some of the complexities. And we've done a lot of work studying hurricane evacuation decision making, including work in Houston and Florida, some of the areas that were just affected. And so we saw this again happen again, that there is that complexity. Some of it is related to the ability to predict different kinds of risks. So there is that uncertainty about the hurricane that's much greater 5 days before landfall, but then some of the decisions, even for emergency planners, they need to start making decisions about, say, they close schools 4 days before landfall, so they can change those schools over into shelters and try to get people evacuated. So I think, for example, in Florida, they knew that they had to do all these things in advance because to get people out from the Florida Keys through all of Florida, perhaps, they needed to start doing these things very early. So they kind of have that in mind, and they need to make some decisions when the uncertainty is much greater. And then as the storm approaches, so as about 24 hours before landfall, they start telling people, get out now, or else just stay. Like, if you don't leave by this time, you need to just find some place to shelter locally. So they stop emphasizing evacuation, and people
stay locally. And then at the last minute with a hurricane, what happens when people are in hazardous situations is it becomes like one of those flash flood situations where the wind, hits your house or the flooding comes up, and then they have to make these emergency decisions. And so there's still that really short time frame decision making. And I think some of the complexity of that is also that, as we saw with Maria and with Harvey, there was rapid intensification before landfall. And so that really complicates the communication and decision making, because meteorologists know there's that potential, but that's not very well predicted. And so you don't have those forecasts 5 days ahead of time. And so that makes it more challenging for people to kind of make the decisions and kind of gear up and mentally prepare themselves to evacuate and so on. So it's a lot of what we're doing now is kind of that interface between what can be predicted at different timescales and what information people need to know and what can they do with those different timescales.
Just going to ask a question about crying wolf. I mean, you could find there are people who say, well, there's been forecasts of this before, it hasn't happened, therefore, why should I act now?
Right, so that's a good question. There's a lot of emphasis in that in the US on, especially for hazardous weathers, for tornadoes and hurricanes. There hasn't been that much research on it. So there is some research that shows, for example, I think it was in 2004, there was a year where there were a lot of hurricanes approaching Florida. People had to evacuate multiple times. And there's some evidence that for people that evacuate from hurricanes, they don't really mind the false alarms. We find that prior evacuation from hurricanes is the strongest predictor in several of our studies of future hurricane evacuation. More powerful than the messages, more powerful than other kinds of things. It's really, even if people evacuate and they come back and find nothing happened, then many of them are willing to evacuate again. Of course, that's affected by the fact that often they see that other areas were affected, it just wasn't them. But then there are some people who, they get stuck in traffic, or people have told me about their bad experiences sitting in a car with their kids screaming, getting stuck in traffic, and they don't want to do that again. And so if that's your most memorable aspect of the experience, then you're less likely to evacuate again. I was talking to someone from Puerto Rico recently who was saying that in the islands, a hurricane can just miss them entirely, so they have a different experience as far as the near-miss situation. A false alarm can really be a near-miss or a close call for you. But that's also a big emphasis in the tornado work that we and others are doing now, where for some kinds of tornadoes in the US, the false alarm rate is really high because they're really hard to predict. And they happen at night, so you can't really see what's going on. And there is some evidence that people start turning off their phones at night, or they're less likely to shelter or so on because of the false alarms. But I think some of it's really about helping people interpret what a false alarm means. Like as meteorologists, we think about it as a false alarm, but really it's a close call, or really some of it's inevitable, that you can't predict where a tornado is going to happen 2 hours in advance. It's just not possible. And so kind of gearing people's expectations for what those predictions mean, and how they should interpret them. And because of that, people do use different information. So they'll look at their environment. Like if there's no thunderstorm outside or it's not hailing, it's not raining where they are, they're less likely to believe there's a tornado. And that's the one way of them dealing with the false alarm issue. So I think it's a really important question, and there's a lot of complexity to it depending on the situation.
Thank you. Basing research on social media, is there any evidence that it's actually having a negative effect in picking up on the last point of false alarms? A lot of people want to be stars and therefore maybe exaggerate or put out false information.
Yeah.
A lot of misinformation leads to disbelief. 10 years ago, when there was certainty of probably 3 days of forecast ahead, we all watched the weatherman on the news, or the weatherwoman on the news, and we believed it, but there seems to be just an overflow of information now.
Yeah, so there is definitely an overflow of information. In the US, in our work with social media, we haven't seen really evidence of that. In fact, if you sort of search for, and I've seen studies that do this, for Hurricane Sandy in the Twitter data, you see a lot of people that are making jokes about the situation, not taking it seriously, and so on. But that's because most of them aren't really at high risk, or there's a lot of teenagers who aren't making decisions for themselves. But if you sort of dig to the people that are at risk and are really making decisions, I think we see a really surprising amount of people engaging with the information and really trying to figure out what the risk is for them. I mean, not everyone, but and people you wouldn't expect. So for example, in one of our studies, we studied this neighborhood that happens to have a lot of rappers in it. And so people are on Twitter because they're trying to advertise their music. But even these people who you think, one of them throws a party 3 days before landfall, but he throws a party because he knows that he's not going to be able to throw a party on Halloween. So he's really assessed the risk and moved his party up. So, he's still surprised when it floods. But I mean, I think a lot of people are really, sometimes we're giving people less credit than they deserve as far as what they're thinking about and what they're doing. I think it is complex because, like, you're right that misinformation can travel more rapidly, and people are looking at that kind of thing. I think especially in the emergency management world. So how do you intervene in the right way? So there are issues with that, but I wouldn't say that's the prevalent story. I think there is that going on, and there are questions about how do you, as an authoritative source like a forecaster or like emergency management personnel, how do you intervene at the right time to correct misinformation when it is propagating really quickly? But we haven't seen much evidence of that, being a major effect in our stories. There is, some colleagues of ours have done some work with propagation of images on social media, and there is a lot of people tweeting a tornado that happened, 5 years ago. Or for the, the earthquake in Nepal, they did a study of that, and people are, they are posting pictures of other kinds of events. But what they find is it's usually not the people that are directly affected, it's people in the surrounding areas that are trying to make meaning of the event, or they're saying like, oh, there was a tornado, and they just tweet a picture of a tornado. But it's not usually the people that are like in the midst of the situation who are doing that, or maybe they're not really engaging with that side of outside world. They're really focusing on the local conversation. So, yeah.
Okay, I think we should move it on, but thanks very much, Rebecca.
Thank you.
So for the next talk, I'd like to invite Becky Hemingway, who's a weather impact scientist at the Met Office, to tell us about their impact-based warning system.
Hello everyone, thanks to RMetS for having me. I'm Becky Hemingway, I'm a scientist at the Met Office, and today I'm going to talk about what is the impact of an impact-based warning. So I'm going to start with a quote, and this is kind of my motivation for a lot of the work I do. It's actually about American hurricanes, but it's people want to know three things. What does it mean to them? What does it mean to their family? What do they need to do right now? And so don't speak to me like a meteorologist. Tell me what we need to know. And this really hits home that people don't want to know just about the hazard. They want to know about how it could impact them. And it gives the why do I care, or what should I care about, really gives it meaning. So for example, let's take these hazards. You've got 50 millimeters of rain in an hour. 60-mile-an-hour winds, or 35 degrees C in the UK is boiling. Or, for example, slightly kind of rarer events, so the low probability but really high impact events like space weather. If you say these kind of things generally to the public, it doesn't really give much meaning. You've got to be a meteorologist to actually try and understand what this could mean. So why don't we change our phrasing of these things to 150 millimeters of rain in an hour will cause flooding, therefore action is required. 60-mile-an-hour wind gusts will cause travel disruption and fallen trees. Gives a bit more context to what does 60 mile an hour mean. 35 degrees C, advice on what to do. It's really hot, so stay in the shade and drink loads of water. And then finally, again, for these really rare events, what might they actually cause? Because you can't actually see space weather apart from as the aurora, but it can cause actually quite severe communication and GPS problems. So if I haven't kind of convinced you enough that we need to do impact forecasting, these are two documents that were both released in 2015. So the first one is the United Nations Sendai Framework. This is 187 nations have signed up to Sendai. And the whole point of the document and the whole framework is to reduce disaster risk across the world by 2030. Now this is to reduce the number of lives lost and also to reduce the amount of cost we spend on natural disasters. Now we've also got the WMO guidelines on multi-hazard impact-based forecasts and warning services. Again, this is 185 different members in this, and in the executive summary of this paper, it really talks about how many lives are lost every year and the big economic cost of the weather and hydrometeorological hazards. So, and then it also goes on to talk about, well, we know we can predict all these really, really well. So why is there this apparent disconnect between us being able to forecast the event and actually knowing what impacts might happen? So it then goes on to talk about a multidisciplinary approach to actually understand the impacts. And through understanding the impacts, we can actually use these documents to really reduce the risk and to save lives and to reduce the damage. So in the UK, we have the Met Office, of which I work for, which is great. We also have the National Severe Weather Warning Service, as you've probably all seen with the weather warnings we issue. And this is the risk matrix that we use to assess what colour the warnings need to go. So in order to assess the warnings, they are impact-based because they use this combination of potential impact and likelihood to assess what the risk might be and therefore where to put the tick and which colour of warning to issue. So for example, this is from last week. We've got a medium impact, a medium likelihood across a certain area around the middle of the country, and this is for wind. You can also put lots of different warnings out at the same time. They're all valid for different amounts of time and different spatial components. And what happens is our meteorologists in our operations centre assess where on this scale the tick should go. So at the moment, they use a combination, so they assess these impacts using a combination of past knowledge of impacts they've seen before, what the event's like, the time of day, which areas it might affect, population centres. And we do have tables available on our website that actually say in which column what the impacts might be for each different type of weather. But they do use a lot of kind of subjective assessments. They talk to the people on the ground that we have, our civil contingencies advisors, but it's really, really subjective. There is not a quantifiable way to assess impact. So this is where hazard impact modelling comes in, and this is what I do. This is what I've been doing for the last 5 years. So I do this as part of the Natural Hazards Partnership. The Natural Hazards Partnership is a collaboration between 17 different UK organisations. Part of the Natural Hazards Partnership is the Hazard Impact Modelling Project, and the aim of this project is to combine data and expertise from partners to identify and forecast the impact on populations, areas and assets from a range of natural hazards. So we all work together, and I'm going to demonstrate this with a couple of impact models that we've created. We all work together, and we all have different specialties. So we pull on these strengths, so we're not repeating the same work, and we are able to do the work more efficiently through these partnerships. So I'm going to start with what actually is a hazard impact model. So you take this equation, hazard times vulnerability times exposure equals risk. So the Natural Hazards Partnership focuses on 3 hazards at the moment, landslides, wind, and surface water flooding. My specialty is wind impacts, and I'm also going to talk about surface water flooding. Now, we use probabilistic models, so we use ensembles, and we look at the probability of thresholds being exceeded. So for the wind model, the thresholds were determined by a modelling study that actually looks at vehicles falling over. So what thresholds do those vehicles start actually falling over? So these are our probabilities that we then input wind gust information into. Second part is vulnerability. So this is looking at what makes an asset vulnerable to a specific hazard. So for example, the proximity of trees to railway lines makes that railway line more vulnerable. The height of a road, for example, a bridge, it's in a vulnerable location because it's not got much shelter. The state of disrepair of a house makes it more likely to be caused for wind to cause damage to it. And also the proximity of housing to where a flood might be. It's also an increased vulnerability. And the final part of the equation is the exposure, which is the number of people, for example, the number of people, cars, or buildings that could potentially be affected by the hazard. These all combine together, and in the hazard impact models, they are all weighted equally, and they combine to form a risk output. So on the right-hand side, we have my baby. This is my vehicle overturning model for January 2015. Now, we take the value that comes out as the risk and we put colours to it because it's a bit easier than just putting a load of numbers on kind of a road network, and it allows us to see how the storm's moving across the country. Now, there's a bit of a story behind this one. So I got into work in the morning on the 8th of January, and this was the National Severe Weather Warning Service warning that had been issued at the time. I came in and I looked at my vehicle overturning model, and as you can see here, they're on hourly time intervals. You can see the storm running across the UK in the evening of during the morning of the 9th of January. So what happened was I kind of looked at the central belt of Scotland around this area here, and it was it's showing medium, high risk. And this, because I look at the model quite a lot, I knew this was kind of anomalous. I hadn't seen this before. So I went down to our operations centre and I said to our chief meteorologist, have you seen what vehicle overturning is doing? It's gone a little bit crazy around the central belt. So what did he do? It's brilliant. He used the vehicle overturning model as evidence to issue and update these warnings. So what he did was he issued a new amber warning because we had evidence that there was going to be higher impacts in this area. And he also pulled the yellow wind warning down towards Cumbria to engulf a different region of what's shown on the vehicle overturning model as well. So this was great. My model had actually been used as evidence. I'm pretty much jumping for joy around the office. And this is what actually happened. So a vehicle went over on a bridge in a precise area where the vehicle overturning model said it was going to go over. I was so happy when I saw this photo of this van blowing over. It was unbelievable. Right in that area, right where the amber warning had just been issued with my model used as evidence. Couldn't be any happier. I also spent the rest of the day looking for pictures of vehicles falling over, and I do this quite a lot. So I scrape social media, I scrape Twitter, I scrape news reports. I spend a lot of my time looking for pictures like this. And when I find one, I try and then locate it so then I can try and validate my model to prove that it's correct or not. This is important. It'll come back up later towards the end of my talk. Second model, surface water flooding hazard impact model. Now, this is a bigger, kind of more complex collaboration between many more agencies and between Natural Hazards Partnership and a few other people that we brought in to help as well. The whole user of this is our Flood Forecasting Centre. So this is how the model works, a lot more complex, as you'll see. So we've still got the ensembles, all probabilistic information. This then goes into the grid-to-grid hydrology model, which looks at surface water runoff. This goes into the hazard footprint, so that produces that hazard footprint I talked about. Now, then you get the impact library. This is made up of multiple different layers of data. I'm going to talk about this again in a little bit more detail on the next slide. The hazard footprint and the impact library, which is the vulnerability and exposure data, combine to produce surface water flooding risk outputs. Now, they're real time because the models update every 6 hours on an hour with hourly forecasts, so they do run every single day, 4 times a day. This is what the output looks like in a visualization system, and it's done on a county basis because the information itself is actually disseminated through the flood guidance statement to responders around England and Wales. So it's done, takes the user requirements into account when it produces the risk forecast, so then they can use it directly in assessing how they should issue the flood guidance statement and which areas need warning, need the guidance given for. So the impact library construction, now I really like this slide, it's really cool. So this is how it was built. So we've got the surface water flood maps from the Environment Agency. We've then got the building information, so where the buildings are, so this is a bit about the exposure. Now the vulnerability is if that building could potentially be inundated by the flood. So here we can see that we're looking at which buildings, and they're all highlighted in pink, the buildings that could be flooded based on this flood map. We then look at the population, of where the population are. We see, for example, if they're more vulnerable populations, for example, in a care home or in a hospital. So we flag these up as more vulnerable. We also look at the depth of the floodwater and assess like how deep that floodwater is going to be for each of those properties. Then look at the road network and see which roads could potentially flood based on the flood maps. And this is a really cool piece of coding that's been put in. But once a section of road is flooded, that entire road is actually taken out. It's kind of gone. This road is flooded. So it doesn't just flood that little bit of road, it takes the whole road out. And what happens is we do it on a kilometre cell criteria basis. So we look at relatively for all the rest of the cells around the entirety of England, which impact severity level is in each cell. So we're looking at how much exposure and vulnerabilities, how many impacts could potentially happen should that flooding scenario occur in that cell. So we've done this working together using all the different data sets that we have, and we've done it for the whole of the UK, the whole of England. And what you can see is generally it's the populated areas, and these are expected because should a flood happen in the middle of nowhere where no one lives, the impacts aren't going to be there. Should it happen in the middle of Newcastle, you'll get a lot more impacts happening. So we need to understand actually where these impacts could potentially happen. So just a summary. So we've got the surface water flooding hazard footprint that we take for where the surface water could potentially happen, combine that with the impact library to produce a regional summary of surface water flooding impacts. And then we use the exact same table as the National Severe Weather Warning Service, but this time it's for floods, to do a regional summary of surface water flooding risk. Now we do this for each ensemble member that we've got within the model. So therefore we can assess the uncertainty of see what each ensemble member is doing and look at the uncertainties in that. Summarize it over space, time and that uncertainty. So it's got some very clever coding in the background, and also we use the experience of the forecasters to add value to these kind of outputs. And this is how it works on a case study, so the 23rd of June. You see two forecasts 6 hours apart, so they do change over time. So this is the most recent one for this scenario. And this is what was issued on the flood guidance statement with a bit more detail in this map here. And this is what actually happened. So again, they go through Twitter, they use the impact reports they get from the social media and news to see if the flooding that they thought might happen actually occurred or not. And that's how they do the verification, very similar to how I do vehicle overtaking. So you can see in general, it did pretty well. So what are the benefits and the challenges of the hazard impact models? Well, they provide objective outputs, which is really good. It means that we don't get any inconsistencies. We don't have, while their experience is really good to have, it means we never have two people with conflicting views. It will always be the same thing because the models are set up in the same way every single time. Can aid decision-making, as I showed with vehicle overturning, and improve preparedness, because the models do run out for a couple of days, so they can start highlighting regions that we might need to look at more in the future earlier on. Improve understanding of natural hazards. It might highlight regions that we've never even thought about impacts happening on before, once we start layering up all the data and actually doing the impact assessment. And it encourages things like the NHP to happen, Natural Hazards Partnership, cross-organisational collaboration to both create the models and also understand how to visualise them and provide them to the users. Massive challenges still. I spent a lot of my time looking at the science of impacts and also how impacts interact with each other. So we could start doing multi-hazard impact assessments. This is a really new area that is really, really complex, and hopefully we can make some strides in the future in that. Data availability. I've shown you loads of data layers, but it's really hard to get. It's surprising how hard some of this data is to get. Timeliness. We need to make sure that the models run and they're valid actually when they're supposed to be valid. We shouldn't have them running for 12 hours because by the time they've run and finished, the forecast has already gone. They've passed the validity time. So we need to make sure that they run fast enough and also are useful. Validation of the models, I've mentioned a couple of times. How do we actually validate this in a way that I don't have to spend the rest of my life looking for pictures of vehicles falling over on Twitter and in the news media? And finally, communication of results. Now, this really is key, communication of the results and the outputs. And there's so many different people we could communicate it to. At the moment, the models just go to expert users and scientists, for example, myself, like a scientist that develops the models and tries to improve them. So, but if we were wanting to communicate them and use them for any of the any other of these categories, this isn't an exhaustive list. We need to think about how we communicate to them and what do they actually mean, and have we actually done it in the right way? So we do need to talk to them. We really need two-way communication. Now, you've had probably enough of me waffling on for now, so we're going to play a game. So audience participation. And this game is called Who Remembers? So wakey, wakey, everybody. So who remembers the 12th of February 2014 storm? 1. Was it a major storm? Leave your hand up, whoever put that. We're not sure, are we? This was only, 3.5 years ago. We're not sure. Actually, it was huge. It was red warnings. These would get issued maybe once a year, maybe twice. We had over 250 flood warnings or alerts over the UK, and it caused kind of mass chaos. 75,000 without power, 100-mile-an-hour winds. It's when the Dawlish railway line in Devon actually washed away, and it cut off parts of Devon and Cornwall for an awful long time. So this was actually a pretty major storm, and no one could actually remember it. I have a point, I'm going to say. Right, next one. Round 2. Who remembers the 15th of November 2013 storm? Nobody again, we're doing well here. Well, okay, no one's got their hands up, so I can't really ask you if it was a major storm. You're correct, it was a red herring. It was actually, there was no storm on the 15th of November. So for the last 2, everyone's, one was absolutely, can be quite catastrophic red warnings, the next one didn't actually happen, and we've got a very similar response. Final one, I promise. 23rd of February 2017, who remembers this? It was only like 7 months ago. A few more. Yeah, what happens if I call it Doris? Who remembers Doris? Hands up. Cool. Was it a major storm? Keep your hands up. Yep, absolutely correct. We didn't have a red warning out for this one. We just had ambers, but still we had rain, wind, snow over most of the UK. And this is what actually happened. Unfortunately, 2 people died. Lots of damage and destruction across the UK. Roads closed, trains impaled, lorries falling over, so I was happy to see pictures like this. Yeah, quite catastrophic. Now, I do have a point to this. I've just told you a date, and now if I said to you a storm like the first one, because I can't remember the date of it, was about to hit you, you wouldn't have a clue. If I told you something like Storm Doris was coming at you, you might actually think, might need to look at the weather a little bit more. And all the storms are named with an impact-based name using the impact-based warning system that we have at the Met Office. I'm just going to show you a really short video of how we name these storms. There's no sound, there's not supposed to be. Right, so they're the storm names for this year. These are all the storm names we've ever had. We work in partnership with Meta in the Met Office to actually name the storm. So it's anything that's going to be a amber or red warning that is going to impact either Ireland or the UK. So we've been doing it since 2015. I think this is a brilliant scheme. I think it's amazing, and I'm going to tell you why I think it's amazing. So you can see also you can see how many storms we had. So we had 11 in 2015, 2016, 5 in 2016, 2017, and I'm hoping for 17 this year, because my name is on there. This is what my mum calls me, Rebecca. I know a lot of people in this room are not hoping for 17, but I really am, because I want Storm Rebecca. So why is it so cool? Why is it so good? The reach of storm naming is amazing. So tweets with a number of hashtags, for example, Storm Abigail, 19,000. You get to Storm Desmond in 2015, 2016, 129,000 tweets with hashtag Storm Desmond on them. And then these are the potential reach of millions and millions of people. People with these things reach like this, people can be so much more aware of what's going on. The weather becomes exciting. The weather becomes something that people are aware of, and therefore they're more likely to think, oh, should I do anything? Should I change my plans? What are the impacts going to be to me? They actually start thinking and asking themselves these questions. It's a slightly different kind of way of showing very similar information for 2016, 2017. You can see again, you've even got things like false Doris. It did happen. People thought Doris was named before it wasn't actually named. It wasn't named till here. But you can see again the reaches in the millions. So millions of people are aware, have the potential to be aware of these storms, and it's great. Think about if you said the storm of the 12th of November 2013 was going to happen. You wouldn't get this. Hashtag storm 12th of November 2013. Doesn't really have the same ring. And we've done some analysis at the Met Office. So Storm Doris, for example, 89% of people within the warning area were aware of Storm Doris. 95% of those found the warning useful. Brilliant. 49% of those took action. So it means they actually changed their behavior based on the warnings and what was issued. Because we named it Doris, because Doris is a cool name. And also, when you sit on the right, we've got some kind of things that were said. So it simplified the message. It's easier to talk to the general public about. And responders actually on the ground really, really like this kind of thing as well. So it makes it easier to raise awareness in the profile of these severe weather. So people are more likely to be aware, therefore they're more likely to take action. So this is a slightly different thing. At the Met Office, we have a piece of software that uses an algorithm to detect if it's an impactful tweet. So it takes, for example, wind, snow, or rain, and then it looks at the tweet and see if it actually has other words like damage or flooding within that same tweet, and it tracks it. So this is what happens for each of the storms in 2015, 2016. You can see some had more than others. This is an example of a couple of tweets for Desmond. And what I can do, think about the impact models I've just talked about. I don't want to spend my life searching Twitter, so this does it for me. It then makes everything easier. I can then see what impacts have actually happened, and I can use, instead of using the 20 that I could find before by myself, the piece of software could give me potentially hundreds or thousands. So this is for 2016, 2017, and I use the same thing for, for 2016, 2017. And this goes up to 7,000. The last one went up to 2,000. So you can see Doris was huge, including planes that crashed on runways. And then just to look, just to kind of see what the other two look like as well, Doris was quite, very up here, exponential kind of thing. And again, you've got a bit of Storm Doris. See, some are more popular than others. Depends on where they hit. So I think Connor only hit Ireland. We didn't really have much about it in England. So that's why Connor had relatively less impact and less tweets. So finally, the last slide. Back to my original question, what is the impact of an impact-based warning? Well, I think that they give more meaningful warnings. You're actually going back to the original first slide I showed you. It answers that question of why should I care and what does it mean to me? If you can give them what the impact might be, then it's more likely to hit home than saying what the weather's going to do. Hazard impact models, like I've shown, they have been shown, as you've seen, hopefully with the examples I've shown you, to provide users with understanding of what the potential impacts could be in a very objective way. And finally, I think storm naming is great. I really, really do. It increases awareness and improves communication, but also it makes my life a lot easier because then I can use the hashtag of the storm name to actually track what's going on, and it makes it a lot kind of really good, and it makes my work a lot easier as well. And I'm going to leave you with Storm Barney because he's cool. Barney the dinosaur. Thank you very much.
Okay, thanks for your questions for
I have had a number of people, by coincidence, say to me recently they're fed up with people giving names to silly little weather irregularities, as opposed to the naming of the big hurricanes that go around the Caribbean, where the naming is helpful to enable people to see which one is being referred to when several are moving around. And the important thing with those is tracking where they're going to go, whether they're going to hit a particular island or miss it. To me, it goes hand in hand with the whole system of Met Office weather warnings. Whenever I look at a forecast, there always seems to be a warning, and it's sort of usually of something fairly trivial, which to my mind, if you're not careful, you can make people almost despise the warnings by warning of things that are too small and naming things which are not noteworthy. Nobody named the 1987 hurricane, which I remember because it nearly killed me. So I just make that comment for your observations.
Okay. So in 1987, we didn't name storms, so that's that one gone, because we didn't name them. We've only just started naming the windstorms, so no one named it. The reason the storm naming started was because of St. Jude's Day storm. It ended up with 7 different names, depending on where you were, which country you were looking at, and which media picked it up. Now, that made it even more confusing to have 7 names. So we decided to, with MET-ERIN, to actually just say, right, we're going to make the messaging consistent throughout the entire media. So that's why we named them. Yeah, there are lots of warnings to go out, but we don't issue warnings willy-nilly. We do definitely think the meteorologists use their expertise to issue the warnings when they think it's necessary, and they do it with the civil contingencies advisors, which are in the ground in each area, and they talk to them and say, right, what would this hazard, what would this rainfall, this wind have affect your area with? And it's just for everyone to then be aware of what's actually going on. So you might feel there's lots of warnings issues, but they are issued with a purpose. They're not just issued because we feel like it. They really do have a purpose, and I sit on a subjective verification group for those, and we do assess each different every warning that goes out to see if we hit or miss, basically, the false alarms as well. And we do have a very good success rate at actually issuing the warnings, and we generally see that the impacts that we thought might happen do happen, and we do have a lot of lessons learned as well. So it is an evolving structure. So I don't think we issue too many at all. They are all valid warnings.
I think I'll take the opposite point of view, Becky, and say that as a broadcaster, I'm a big fan of naming storms. And I thought you actually showed how effective it is at getting the message across in some of the slides you had there. My question, though, is about something slightly different, the vehicle overturning model, and how you communicate effectively the results from something like that. You have there a very detailed tool that's giving some really good results. That then gets turned at the moment into a vague orange blob on a map. Now, for that poor lorry driver whose vehicle was lying at the side of the road that you're enthusing over, for that driver, you know, why can't they get a text on their phone which says, you're at risk when you're going to be driving up that bit of road that your vehicle's going to overturn? It feels like you've got a really powerful tool, but you're downgrading that information in terms of actually getting it across to the end users. Yep,
great question. So the Natural Hazards Partnership is all government. So the vehicle overturning model was made for the Public Weather Service, and therefore it feeds into our operations centre where it is used to aid decision making. However, I've presented it multiple times over the last few years, and I am in talks with Highways England, Transport Scotland and haulage firms who are obviously very interested in it as well. We need to understand what the users require to see actually if it's suitable for their needs, and if it needs modification, how it needs modifying. So yes, great point. We are looking into things like that because I think it is a very valid thing to do in that world.
Thanks very much. Yeah, really great presentation. And I think you showed really well the tie-up, the intricate tie-up between yourselves and the emergency responder community. I'm going to sort of plant into the room a big elephant, and to me that's fog. Because I would argue that, I mean, I don't have the stats to back it up, mind you, but I would argue that more people are killed by fog, or, you know, traffic accidents caused by fog, than wind and rain on many occasions. And I know, having worked in the Met Office for many years, I know one of the reasons don't warn for fog. Well, there are two reasons really. One of them is that we're not very good at forecasting it, and secondly, the emergency responders, the contingency community can't actually do anything with that information. They can't tell people to do something, and they can't it's not a call to action for them, which leads to warnings not being issued. And anecdotally, and my colleagues feel as well, that we actually don't warn enough for fog. And perhaps I slightly agree with earlier questioners that we do slightly over-warn for other elements. I just wonder what your thoughts on that were.
I know we're not brilliant at forecasting fog, so that makes it really hard to warn if we don't know where it might be. We've just got to think, and this is not what we do at the moment, but maybe what we should think about doing in the future is how to communicate the message that we are really uncertain that it might happen, and give advice. For example, maybe slow down when you're driving and you see fog. So more public information of what the impacts of fog might be. So that could be something for the future to do that. As I'm not a meteorologist, I don't feel I can answer your question kind of in any better way, and I'm not a forecaster either. But I take your point on board, and I'm happy to discuss it with you later.
Okay, I think we'll have to move it on from there. So thanks very much, Becky. So the final talk of this session will be given by Kelsey Mulder from Risk Management Solutions.
Hello, I'm Kelsey Mulder. I currently work at a catastrophe modeling company called Risk Management Solutions, but today I'm not talking about catastrophe modeling. I'm instead talking about some research that I did while I was working at the University of Reading and worked on with Andrew, who's been hosting us today. So one of the things we were looking into was in terms of communication. So some really big general questions. How do we communicate uncertainty and risk to users? And how do different forecast representations and design decisions affect users' decisions and data interpretation? So in a sense, we were looking at really fiddly little things. Do little tiny decisions in your design of a forecast affect how people make decisions based on that forecast? So these are quite generic problems, and they're actually relevant to a whole host of different hazards. And we focus specifically on maps and on line graphs, because these are really common ways that we communicate weather information. So how we research this for what we call decision games. It's essentially a survey. Our respondents were given a situation, and were asked to make a decision based on some information we gave them. Now, we fiddled with the information a little bit to see if we could get their decisions to change based on what we were presenting. So I'm going to present a couple of different decision games that we did. The first one I'm going to talk about was based on volcanic ash flight decisions. So you may have remembered the 2010 Icelandic volcanic eruption. It disrupted air travel for a good few weeks. And so we had a meeting in February of 2016, and we invited 25 delegates who are experts in both research on volcanic ash as well as operations. So we had flight planners, airline manufacturers, airline representatives, pilots, and employees of the Civil Aviation Authority. So what we did is we gave them 3 different forecasts. The one on the far left, this one, is the official forecast that people in operations on flights are given when a volcano erupts. And what it shows is just a plain basic polygon, and it represents the outermost extent of volcanic ash. Now, the Met Office heard some feedback from some of their consumers, and granted this eruption occurred in very heavy, busy airspace. There were quite a lot of flights that maybe could have happened but did not happen because of kind of this basic level of information here. So the Met Office trialed a bit of a product. Volcanic ash is safe to fly through at certain concentrations. So what the Met Office did is they made 3 colors. They did this blue color, suggesting this is a safe level of volcanic ash to fly through. This gray color shows levels of volcanic ash that are safe to fly through if you've passed certain safety tests. And then this red area is unsafe concentrations of volcanic ash. Now on the far right, this is kind of a new and up and coming way of actually observing volcanic ash. It's by satellite observation. So we wanted to trial this as kind of a higher resolution. So you can think of these forecasts as kind of low resolution to high resolution, and we wanted to see how decisions changed. So one thing we did with our delegates is we presented them a forecast, and we said, draw an area with this pen around this forecast that you definitely would not fly through. So in the black outlines here in the middle, that's the actual area of unsafe concentration, so equivalent to this red area here. And what you see in red is what we kind of call a heat map. So we overlaid all of the different drawings on top of each other. So the darker red areas are where a lot of people said they wouldn't fly. And these really light outlines out here that you can barely see are where very few people said they wouldn't fly. And what you may see is that most people drew no-fly zones that were much larger than the areas they were told were unsafe to fly through. So similar to what Rebecca said earlier today, that people are indeed inferring uncertainty into forecasts where uncertainty isn't actually given. But again, similar to what Rebecca said, the amount of uncertainty people are inferring into the forecast is not the same. Between different people, there are a whole different range of uncertainties. So what's plotted here are different areas of the no-fly zones that people drew, and there was a wide range of how big they were. So we also wanted to see how this different kind of level of resolution affected people's flight decisions. So on all of these forecasts, we gave little flight plans, and we asked the delegates if they would fly on these various flight plans for these different forecasts. And what we found is that with more information, the delegates were more risk-averse in riskier situations. They were less likely to fly in riskier situations, and they were more risk-seeking in safer situations. So in a sense, they were making better decisions with more information, which is good to know. And they actually explicitly said that they wanted more information. So about 50% of the delegates said with this polygon information explicitly, I need more information to make a decision, compared with 16% when you give them a whole lot of information with the satellite observations. Well, we sat on this information for a while and had a few thoughts and thought, well, let's try again. Let's try it again with a different hazard. Again, as Rebecca was talking about today, people have this kind of preconceived notion with perhaps the temperature forecast that they see every day of what kind of uncertainty is around that. So we thought maybe we can control for that. So we gave a situation that perhaps nobody has seen before. We told people that they were in the situation of a manager of a vegetable company. And that vegetable company had to ship vegetables across a strait. That strait is often icy. So they basically had to choose how big of an ice-breaking ship they had to send out. So they had to decide if they were going to send a small ship, which could break through ice up to 1 meter thick, or a large ship that could break ice over 1 meter thick. And then there was a loss of product and kind of a monetary loss if there was a wrong decision. They were given ice thickness forecasts, and there are no real such thing as ice thickness forecasts, so that's kind of where the kind of preconceived notions are taken out of the equation. So we gave them the forecast in a number of different ways. We gave them kind of a verbal probability of ice thickness greater than 1 meter. We gave them a basic line on the graph, which kind of represented a median, kind of a middle value that was expected. And then we tried giving uncertainty in 3 different ways. So we did what's called a fan plot, which shows different percentiles of ice thicknesses over time. A spaghetti plot, which shows kind of out of 10 situations, what could the possible ice thickness be? And then a box plot, which also shows kind of likelihood in the spread of the ice thickness. So we conducted this decision game in a couple of different ways. We wanted to target experts again, like we did for the volcanic ash survey. So we did a paper-based survey with atmospheric scientists. But we also did an online survey for 2 reasons. One, we wanted to target the public, the general public, and see what they thought. And we also wanted to target actual decision makers, so people in industry who are using these forecasts to make decisions. So think about maybe the energy sector. You need more energy if it's cold out, so they look at temperature forecasts even up to a month in advance, and then they decide on how much energy they can buy and sell and prepare for these kind of cold events. So we targeted people like them as well. So the first thing we looked at, like I said, little fiddly bits of the forecast, are whether or not this little median line is present. What do people do with the median line? And perhaps unsurprisingly, if you ask people how thick the ice is going to be, and you give them a median line, they pretty much tell you what the median line value is. Give a person a line on a graph and they'll read it for you, so that's not very surprising. And if you don't give it to them, they're a bit different. And there is more variance in the best guess forecast if you don't give them a median line. Again, this isn't terribly surprising stuff. We wanted to verify some of this with what's called eye tracking. It looks a lot more terrifying than it is. We affix this device to their head. It follows your pupil and watches you take the survey as you take it on a screen, so it shows where your eyes are actually going. So this is an example output. These little blue dots show where this individual was looking when they were taking this, this survey question. So you can see they've read the question, they saw the two options, they maybe looked at the axes of the graph, and then they looked at the key a little bit, and then they looked around and came up with a decision. So we compiled all the information from all of the eye tracking data and produced this heat map. So again, these red and orange colors show areas where people fixated for longer. And by fixation, I don't mean just looking around everywhere. You have to actually look in one place for more than about a second or two. So without giving them an anchoring line, asking them what decisions they would make, they looked at all of these possible options on this spaghetti plot and then came to a decision. Now what happens when you add the anchoring line, the median line? Well, they don't look around that much, do they? They go straight to the line. So this kind of proves what we were thinking, that you give people a line on a graph, they look at it, and they give you the answer. So when you compare them next to each other, it's quite the stark picture, isn't it? And again, we looked at kind of the y-axis and where people were looking and ran some statistical analyses. And again, the eye fixations were significantly closer to the location of the anchoring line when we provided that anchoring line. So again, that's not super groundbreaking stuff. People look at lines on graphs. But what gets interesting is when you ask them what the maximum possible ice thickness could be with a graph, does anchoring affect that? And it does indeed. When you give them an anchoring line, the median line, it resulted in an underestimation of maximum values. So again, we had to look at this on the eye tracking map. So when not given an anchoring line, they're typically fixating on the upper end of these graphs. And when given an anchoring line, it does draw the eye towards it, which is not necessarily helpful if you're trying to come up with a maximum possible value. So again, looking at these two next to each other, you can see that people's eyes were kind of drawn towards the line. And again, we did some statistical tests, and indeed, the eye fixations were significantly closer to the location of the anchoring line when it was provided. Another thing we looked at when we did the eye tracking survey was the amount of time it took people to make a decision. So we looked at both decisions, so large ship, small ship, how thick they think the ice is going to be, their best guess, as well as the maximum possible ice thickness. So when asked for the small ship, large ship decision and their best guess forecast, it took less time to complete the decision when they were given an anchoring line, but it took more time to complete the task to guess the maximum ice thickness when given an anchoring line. So again, this gives a bit more evidence that the anchoring line really draws your eye to a certain value, whether that value is helpful in your decision or not. So another thing we tested were the difference in ways you can show uncertainty information. So perhaps in this 30% chance, the spaghetti plot, this fan plot, and the box plot. So looking specifically at maximum ice thickness, the experts guessed a maximum ice thickness as the same as what was shown on the spaghetti plot and the box plot. And the maximum they showed for the fan plot was larger than what we had shown. Non-experts guessed a maximum the same as what was shown on the spaghetti plot, a maximum larger than what was shown on the fan plot, and then a maximum lower than what was shown on the box plot. So a bit of context, we gave them a key for these plots. Specifically for the fan plot and the box plot, we told them that it's the range between the 10th and the 90th percentile. So if we gave you a fan plot, the maximum should actually be higher than what was shown for the fan plot, which both the experts and non-experts got correct. But both experts and non-experts did not get the box plot correct, because they should have guessed a maximum higher than what was shown on the top of the whisker, but neither experts nor non-experts did. So we again pulled in the eye tracking data to figure out what the heck was going on. So we were wondering, do people actually look at a key on a graph if you provide it? And we found that for the fan plot, people actually did look at the key, both in terms of fixation time and the number of times they fixated, so the number of times they looked at the key. But there were fewer fixations and less fixation time on the box plot. So that perhaps indicates maybe some of the reasons why that people were correctly interpreting the fan plot and not very correctly interpreting the box plot. So another question that a lot of scientists are asking is, does uncertainty information affect your confidence in decisions? One thing we tested was providing an anchoring line when we were giving these uncertainty forecasts. There was actually no difference in confidence for non-experts with or without an anchoring line, and the experts were more confident when given an anchoring line. In terms of forecast design, there was actually no difference in confidence between experts or non-experts in their decisions, so they didn't feel any more or less confident depending on how we presented the information. But we did ask them subjectively if they found uncertainty information useful and important, and indeed both experts and non-experts alike found uncertainty information highly useful and highly important. So I'm going to go back again to the volcanic ash survey. It was kind of a unique environment because we only had 25 delegates taking the survey, and they were all experts in the field. So we took that opportunity to have a bit of a chat about the way volcanic ash information is communicated. And one individual commented, I have a fundamental problem using forecast uncertainty. If the best people in the world, the volcanic ash advisory centers, are not confident, are you really going to take the risk? And that kind of spurred a bit of an interesting conversation. Some past research has shown that uncertainty does indeed help decisions, and scientists are quite keen to share uncertainty information with users. But some users actually say that they prefer to use deterministic forecasts. And there was one individual in the group who stood up and said, I don't want uncertainty forecasts, I just want the deterministic forecast. So we poked a little bit more, and it came to pass that this individual also pays for additional volcanic ash forecasts. And he said, well, I look at the official one, and then I grab all the other ones, and then in my head, I compile them together, and I figure out what the actual area is. And you could feel the tension amongst the scientists in the room, because they're all like, we're trying to give that to you, and you're doing it yourself. So we kind of got into some of the underlying reasons for this, and this is perhaps the use of the word uncertainty, because uncertainty kind of has a negative connotation. I'm uncertain about the information I'm giving you. And perhaps a change of language in confidence or error or range of options might be better suited. Right, so what? I've shown you a whole lot of results from a whole lot of different studies. So what's the important take-home message? Well, communicators should not be afraid to show uncertainty information. We've shown, and past research has shown, that both experts and non-experts alike are able to interpret uncertainty information correctly. And to help people make decisions or focus on a middle value, sometimes using an anchoring line is quite useful, but only if extreme values are not important. If extreme values are important in data, especially with a non-expert audience, perhaps avoid using the anchoring line and consider ditching the box plot. So an example of a situation where extreme values are important, that's quite apt right now, is hurricane winds. You're maybe not so concerned about the average wind speed over a couple of days, but perhaps more interested in those really peak gusts as a hurricane makes landfall. So this is kind of a roundup of the results that we had. So there are indeed some structured ways to help ensure the message you send is the message that you receive. So users do infer uncertainty even when it's not explicitly given. More information led to better decisions, especially with the volcanic ash survey. The anchoring line did help guide experts and non-experts toward the particular value, but it impeded them reading extreme values. Non-experts tended to misinterpret extreme values for box plots, so fan plots and spaghetti plots were more useful in those situations. And then finally, just this discussion about the word uncertainty and perhaps other language should be used in future. I'm happy to take any questions you might have.
Okay, questions for
I would only just say that I do think the word uncertainty creates uncertainty in people's minds, and something like confidence factor, a different choice of wording would often make a lot of difference.
Thank you for that.
Okay, seems like everyone. Oh,
So thanks for your talk, it's very interesting. While the sort of free talks have been going through, I've been thinking about whether there's a bit of a subtlety going on here in terms of how we use uncertainty information. So if you have a deterministic forecast, then you can sort of, draw some sort of extra tolerance around it. That's sort of how forecasters typically use that type of information. With an ensemble, you can actually generate the probability of something happening, and that something can be very unpleasant. And even the very low probability of it happening might lead to you sort of blocking off airspace or something like that, using the volcanic ash example. So I suppose, has anyone really thought about the potential consequences in terms of the decision process to a forecaster, where they may be in a situation of almost discounting a probability, however small, of something unpleasant happening, and then potentially that unpleasant thing happening, if you see what I mean?
Yep. So from every forecaster I have ever met, they have definitely paid attention to these low probability events. Ensemble forecasting is not new as of this year. It's been around for a little while. And they definitely look at these kind of tail end events that are unlikely. And kind of going back to what Becky was talking about, they look at the impacts of these, and if warnings are necessary, they definitely put them out. I think one of the things we found in our research was a concern about, so like you said, people do infer their own amount of uncertainty. Part of what we were trying to figure out is, can you confine that amount of uncertainty to what the uncertainty in the models and the uncertainty the forecasters are looking at is? So that's kind of what we were trying to focus on.
Yeah, thank you. So when we make forecasts, we score the forecasts, so we know sort of, what their skill is. Are you able to sort of quantify numerically the loss of information in transmission, from the forecaster to the user? Maybe there's a way of doing it by, getting them to make a decision with some kind of cost-loss model or something that could actually, quantify that. And sort of, we'd be able to put it on the graph with our forecast to see, where the biggest loss of information is.
Yeah, that would be interesting. And it's kind of similar to the question that Becky got with the vehicle overturning model as well, isn't it? That kind of loss of information would definitely be interesting for future research.
Just a very quick one, just to point out what we all know, that model probability is not true probability. So the model will underdo the extreme ends, for example.
Okay. That seems like a good point to go to.
I mean, I agree.
Have a discussion. So, thank you to all the speakers this morning, this afternoon rather. Please be back at 20 past 4 for the second